Okay, let's continue. So now, present value of an annuity. So we consider an ordinary annuity, so an annuity that pays at the end of each period. So the annuity here makes T cash flows made at period 1, 2, 3, 4, 5 up to T. Okay, so the end of the first period is equal to time 1, the end of the second period is equal to time 2, and so on. So there are a total of capital T cash flows. The cash generated by the annuity is denoted C, and the discount rate between periods, between each period, is equal to R. What is the present value of this annuity? So let's look at it step by step. Okay, so standing at time t0, the present value of this annuity is equal to the first payment discounted over one period plus the second payment discounted over two periods plus the third payment discounted over three periods, and so on. The payment number t minus 1 discounted over t minus 1 periods plus the last payment at time capital T discounted over capital T periods. Okay, how many payments? 1, 2, 3, 4, 5, 6, 7, 8. T minus 1 capital T. So a total of T payments. So we have all the payments here in this equality here. Now, can we simplify this equation? Okay, so we are looking for the value of P, right? And note the following: there is something special about this summation. This is a summation of a, this is a geometric summation. So there's a term here which is to the power 1, to the power 2, to the power 3, and there's a way to play with this type of summation. So let's do it here. So note that 1 plus r times p is equal to 1 plus r times the summation. Okay, so here this is the summation, this is the summation. And if I multiply by 1 plus r is the term that is being put to different powers. So we multiply by 1 plus r, and that gives us c plus c over 1 plus r, and so on. Now these two 1 plus r times p and p, they have many terms in common. So they both include c over 1 plus r, c over 1 plus r to the power 2, c divided by 1 plus r to the power 3, and up to c divided by 1 plus r to the power t minus 1. Which means that if I take 1 plus r times p and I subtract p, a whole bunch of terms will disappear. Okay, there's c plus c over 1 plus r plus c over 1 plus r to the power 2. This guy minus this guy, 0. This guy minus this guy, 0. This guy minus that guy over here, 0. This guy minus this guy, 0. So there's going to be only two terms left. See all the terms in red here. So 1 plus r times p minus p is equal to rp. Okay, this is p plus rp minus p. So we are left with r times p. It's equal to c plus a whole bunch of terms that disappear minus c divided by 1 plus r to the power t. So r times p is equal to c minus c over 1 plus r to the power t. So this is, and if we put r on the other side of the equation, so we obtain the present value equation for an annuity. Good. So when we have an ordinary annuity that makes a regular payment C at the end of the next T periods, what is the present value of this annuity? So C divided by R times 1 minus 1 over 1 plus R to the power T. What if this is an annuity due if we consider an annuity generating a total of T cash flow at the beginning of the next T periods, so we have C at time 0, 1, 2, 3. So to have T of these cash flows, the last one must take place at time T minus 1. Okay, so if we count starting at 0, we have 9 fingers. Okay, 0, 1, 2, 3, 4, 5. So counting at 0, the last finger of the first hand is 4, and the last finger of the second hand is 9. So if we start counting at 0 and we have T cash flows, the last one takes place at T minus 1. So what is the present value of an annuity due? So it's the discounted value of all the C's that will be received at the beginning of the next T periods, which is 1 plus R, the value of the annuity paying at the end of the next T period. So 1 plus R times the present value equation for an annuity that pays C over T periods at the discount rate R. Okay? What is the future value? Well, the future value, we have if we remember the equation for the present value, what's the future value? The future value is present value compounded over T periods. So present value is C over R times 1 minus 1 over 1 plus R to the power T. But future value is present value multiplied by 1 plus R compounded over T periods. So the future value happens, so we can simplify this equation. So the future value happens to be C divided by R times 1 plus R to the power T minus 1. This term here without the cash flow. So the term depending only on the number of periods and the discount rate is often referred to as the present value interest factor for an annuity, PVIFA. And if the size of the cash flow is C, the present value of the annuity paying C over at the end of the next T periods is C times the present value interest factor for an annuity when the interest rate is R and the number of periods is T. And the term 1 over R times 1 plus R to the power T minus 1 is often referred to as the future value interest factor for an annuity, FVIFA. And as we have seen before, FVIFA is equal to PVIFA times the future value factor. Okay, here's an example. So an investment offers $2,250 per year for the next 15 years. The first payment taking place 1 year from now. The required return is 10%. What is the present value of this investment? So if we apply the present value interest factor for an annuity with an interest rate of 10% and 15 as the number of periods, and multiply it by 2,250, we obtain a present value of $17,113.68. A bank offers a $25,000 7-year loan at 11%, being reimbursed with 7 equal payments made at the end of the next 7 years. What should the payment be? So the value of the loan is the present value. We are looking here at, we are looking for C, what's going to be the annual payment, yielding a present value of $25,000 when the PVIFA is calculated using 11% as the interest rate and 7 as the number of periods. So that gives us an annual payment of $5,305.38. How long does it take to repay a $25,000 loan with fixed annual payments of $4,000 at 11% annual interest rate? In this case, we will be using the natural logarithm to solve this problem. Okay, so we take the present value equation and we isolate capital T using the log. So T is equal to the log of 1 minus R times present value divided by C divided by the log of 1 over 1 plus R. Okay, so we just rearrange everything such that we have an object to the power T is equal to whatever. So we take the log of the object to the power T, and that allows us to take T in front of log of the object is equal to log of whatever, and T is equal to log of whatever divided by log of the object. So here in this example, so it would take about 12 years to repay such a loan, and the last payment would be less than $4,000. And what is the interest rate? That allows us to repay a $25,000 loan in 10 years with fixed annual payments of $4,000. In this case, we cannot find an analytical solution. We have to use either a computer. So we have to use a computer or go by trial and error. Okay, so in this case, if we use a financial calculator or Excel or whatever, it gives us an interest rate of 9.61%.